Hi there and welcome to this new video. So in this video I want to talk about compilation, and specifically I want to talk about the compilation process as it happens in the C programming language. So the focus is going to be understanding C, understanding how to program in C. Now I have started a series on C where we build the text editor Kilo. I will continue that in the future, so there will be more episodes. But for now I want to talk about compilation. Now, first of all, let's define some terms. Let's understand the difference between compilation and interpretation. Now, over the years, computer scientists have developed diverse strategies to encode computation through languages. I mean, when you write a program, what you're doing is you're encoding a specific computation, and the tool that we have at our disposal are programming languages. Now, to execute a program means to read and interpret the code of the program to obtain an effect over a given system. We have our systems, our system have a state, this state is made up by our hardware, and we can control this state through software by languages. Now, how do we obtain this? How do we write these languages? Well, a very powerful technique in order to obtain powerful languages is translation. And basically the idea is that a high-level abstract language is translated into a low-level language that is more efficient but harder to use. So basically that's the whole idea. We want to write in high-level abstract languages, yet the code that we write has to be translated into low-level languages that can be executed by our hardware. And so here comes the concept of translation, which just implements this abstraction, basically, the way we go from one high level to one low level. Now, this concept, of course, can be implemented in multiple ways. And these are two possible ways, interpretation and compilation. In reality, there are many more shades into this. There's much more complexity in here. But basically, we have two main point of views here. Interpretation, where we have an interpreter that reads the code and executes the code line by line. And if you want to know what is an example of an interpreter, well, Python is an example of an interpreter. When you open Python like this, you are executing the Python interpreter. So here, for example, you can say name equal Leonardo. Then you can say print hello plus name, and here you can put a space. So each line we execute is going to be read and interpreted by the interpreter, read and executed by the interpreter. And this loop is called a REPL, which stands for read eval print loop. And by the way, this concept comes from Lisp, but that's a different story for a different day. So basically we have interpretation where our interpreter reads and executes code line by line. And then we find the concept of compilation, which C implements an example of compilation because C is a compiled language. When it comes to compilation, we don't have an interpreter, but we have a compiler that reads the code the same as the interpreter, but this time, instead of executing the code line by line, the compiler will generate an entire new file, which is going to be called the executable, the process of compilation. And the executable code can then be loaded into memory and executed in the machine. So as I said, here I just mentioned about interpretation and compilation, there are certain contexts, certain implementations which sort of like create a more complex scenario. For example, consider Java, the Java programming language. Now, when you program in Java, what you're doing is that you're writing a .java file, right? Then this file is compiled into a bytecode. So we do have a compilation step. However, this bytecode cannot be directly executed on the hardware, on the processor. When we execute bytecode, what we are doing is we are feeding it into the Java virtual machine called the JVM. And so the bytecode is interpreted by the JVM. So it means that in Java, we actually find both of these things. And the difference is that when we compile a Java file, it is something that can be executed in the machine, but in this case, we are referring to the Java virtual machine, and the Java virtual machine is an interpreter in terms of actual implementation. It is a software that implements the ability to read and execute bytecode, Java bytecode, basically. So that's a general introduction. Now, when it comes to C, what do we find? Well, C is a compiled language, and it is a very powerful language. Now, in my opinion, C is extremely useful to learn about programming, to learn about computer science, because it offers few yet powerful abstractions. Now, you can find C anytime resources are scarce, and here are scarce like this, and you need to control, and you need to have full control over the computation. This, for example, happens in operating systems, in embedded systems, in general, when you need to have low-level control over the system you're programming. C is extremely useful. And basically, modern technology is sort of like built on top of C. Like C is one of those long-standing languages that have managed to really spread across the technical and digital infrastructure. So basically, every piece of technology, if you go deep enough, you will find some pieces of C. Now, in a Linux system, we have the GCC compiler, and here, for example, is a hello world example, really simple. We include the standard input-out library, we define a main entry point, and we call the printf, which just prints this string, right? So we can compile it and we can execute it with the GCC compiler. Now, what I want to showcase in this video, though, is how this compilation process works, how it is implemented, how can we divide it into meaningful steps. And basically here we find the 4 steps of compilation. The first one is the pre-processing, then we find the compilation itself, then we find the assembly, and then we find the linking. Now, when we are talking about compilation, we are referring to the second step, which is the main part of translation. However, the entire compilation process is a little bit more complex, and it also involves these other 3 different aspects, which are extremely important. So let's get started by talking about pre-processing. Now, the preprocessor is a process that executes before compilation happens, and it is used to resolve specific elements that are offered by the C programming languages. And these are macros, includes ifdef and ifndef directives, and also the preprocessor is used to remove the comments. So, to give an example of how the preprocessor works, let's consider this simple code snippet. Here we are including the standard input-out library from the standard C library. We are defining a bunch of things like a variable pi with this value 3.14159. We are defining this square macro that has to be expanded as follows. So basically, anytime you see square of x, you have to substitute that expression with this new one, where x is multiplied by itself 2 times. Then we find a definition of main. Notice here how we are using these symbols that we have previously defined, and the preprocessor, as you will see, essentially swaps, like it just resolves this symbol to its value. It's a simple symbolic substitution, and it can be very powerful. And notice finally these ifdef or ifndef directives. Now these directives are used to include specific code segments conditionally depending on the definition of certain symbols. For example, if the debug symbol is defined, we're going to include this piece of code. Otherwise, we're going to include this other piece of code. Now, let's take this and let's write it into a file called preprocess.c. Because to test this out, you need to just try out in practice. So let's exit from this because we don't care about this. Let's open here org mode and let's do this. So let's preprocess. We can use GCC to stop the compilation process at any of these 4 different steps. For example, if you do the flag -e, it's gonna stop at the preprocessor step. So it's gonna activate the preprocess and then stop after that. So we can do this, and notice that we've created this preprocess.i file, this one, right? Now, if we open it, look at this. Now, this file looks very different from the one we started. So I'm going to put the one we started on the right and the one that we receive on the left. So this stdio.h got resolved with this thing. So this is all the stdio. And notice that it's a little bit of code. It's a bunch of code. All of these come from the standard input-output. At this point, when we go down enough, we're going to hit the main. Look at this main. Here it's going to say preprocess.c. We have the main, and look how the main got resolved. So first of all, we do not see the defined pi and square, but we see them substituted in the code. The value of pi, 3.1, and the way that square expanded into radius times radius. Now notice also that of these 2 choices, basically, we selected the second, that is the printf, the regular printf with the area of the circle and not the debug statement. Why is that? It is because when we generated this code, we did not specify the directive debug. Now, if we want to specify the directive debug, we can do -d debug, so we can do this, and if you do that, with the -d debug, basically, here the code is going to change, and at the end, we will find the debug statements, because during the pre-processing step, the debug symbol was defined, and therefore this if-def was correctly executed. That is, this code got included. Now, why is this needed in terms of C process? Well, this is needed, for example, when you want to hit multiple platforms and you want to have some code that executes some of the time in certain builds and not in some other. Or for example, for debug builds. So there are a lot of reasons why the preprocessor was added. It is not extremely powerful, yet it has some power and one must learn how to use it if you want to learn how to program in C. So that's the first step, the pre-processing step. By the way, if you're interested in learning about web application penetration testing, that is, if you're interested in working in the security industry as a web penetration tester, I have created a course to help you get started into the industry. For right now, it's present on Udemy. It is called Practical Web Application Penetration Testing, and in this course, we show how to find, exploit, and explain 40 security issues in web application. Now the course is extremely practical. We will perform a real test over an application and we will document every vulnerability that we find and exploit through proof of concepts. Now here you can find already some lectures in preview, like this one, SQL injection, and also here in authentication you can find an authentication bypass. Are you interested in working in the security industry? Do you want to learn how to test the security of a web application? And do you like hands-on practice-based learning? If you answer yes, then this course is for you. Because in this course, I show what it means to perform a penetration test over a web application exactly as it would happen with a real client in a typical week of work. This approach, I believe, will allow you to quickly reach the experience level of a junior penetration tester. Go and check out the course, link in the description. Thank you very much, and let's continue. Then we find the second step of the compilation, which is called compilation, and this is the main step of this compilation. That is, in this step, the translation element is introduced, and here we go from the C code to the assembly code. We can see, for example, from this hello world, we obtain this assembly code, where we have information about the file, information about the string hello world, and the code that calls the routine, like in this case is puts, to put the string, because we don't have any format string, but it could also be printf if we had some. So basically, this is the main translation process. We go from a high level. I mean, C technically, from many people, it is not considered a high level, but actually it is a pretty high level language, to an assembly, which is low level language. And to be honest, this assembly, of course, depends on the processor that I'm dealing with. For example, in this case, is x86 64. This kind of assembly. It is instructions that our processor can actually execute. Now, though, and by the way, to obtain this, you can just compile with this flag -s, and then here you can also specify the syntax that you want to write the assembly in. For example, in this case is Intel. By default, it actually prints out AT&T syntax, so that's different. For example, in this case, you just specify -s, and out you have your assembly code. Now, if you do that, for example, I don't know, let's take this, let's define hello.c here, and then let's do gcc-s hello.c. Now this we get an hello.s, and if you do file on this, we get an assembler source, hello.s. So we obtain this thing, and this thing is still source code. That is, we cannot directly execute it. So in the second step, we've gone from the C code to the assembly code, yet we're still talking about code. Now the next two steps will transform the assembly source code into an actual executable. And this step, once again, is divided into two different steps. First is the assembly step, and then we find the linking step. Now, in the assembly step, we will transform each single assembly source code into an object file, into a so-called relocatable object file. And this is sort of like a compilation unit. You can think of compilation in terms of single object files, and then these object files will get linked together in the final step of the process. So if you just want to generate the object file for a given source, here you just do gcc-c. And in this case, if we do it, gcc-c hello.c, notice that now we obtain an hello.o. And if you do a file on this, we obtain, it is already an L64-bit. So that's a big step because we're getting closer to the final binary executable that can be directly loaded into memory and executed by the CPU. However, first of all, we cannot execute this directly. And even if we made it executable, this simply wouldn't work because it is not the correct format. We are getting there, but it is not the correct format. So we can remove the executable bit from this. But look at this. If you open it with Emacs, for example, or with any text editor, notice that now we get a binary file. This is no longer a text ASCII-based or UTF-based file. It is a binary file. So we are getting closer to the final binary format. And this, now in a single project, you have a single file, you have a single object file. Now in a big project, you will have many different object files. Each object file is a compilation unit, and it is compiled independently from the others. Now, by the way, to compile the object file, for example, let's consider this situation. Here we have a load.c, right? Here we have a load.c. Let's say that we have a library. Let's say that we have a lib.c. And in this lib.c, we're implementing some kind of sum function, right? We're implementing something like this, return a plus b. So we're implementing some function that we want to expose to different source code, right? We want in the law, for example, we want to say a hello world and we want to say, for example, sum the 5 of 5 is equal to percentage %t, and then we want 5 the sum like this, right? So how do we do that? Because look at what happens. If we compile the hello.c, it's gonna say, look, you did not define this sum. I have no definition of sum. So what is the idea? Well, in this context, what happens in C is that you will find not only implementation files.c, but you also find library files.h. And these library files, what they do is that they contain the declarations for the different functions, and then they also declare basically if not def, like libh, and then I say define libh, and poi here and if. So basically here they are defining a symbol so that this declaration is only put once. So basically you have this kind of stuff, and then in the source code, you're going to include the h, like this. Now, if we compile it again, notice that I am able to obtain the object file from the hello, even though I still did not tell hello.o what is the implementation of sum. Now, at this layer, there is no implementation of sum. Why? Because the implementation of sum actually lives in the lib.c. So the next thing I have to do is I have to transform a lib.c into a lib.o. So look at this now. I have a hello.o, a lib.o, and the final step will be to combine this object file so that my hello.c, this one, will find the correct implementation and will be able to execute what is sum 5 of 5, which will take it from the object file of lib, from this other compilation unit. And this is why, by the way, we need the last step. We need the linking step. Now, in linking, the various object files of a program are put together to create a final executable. So let's look at how it works. It's pretty simple. You just do gcc, you put all the object file, and then here it creates a default a.out, or here you can also put -o, and you can say main, for example. And you can create an arbitrary else binary. Now in this case, this is a total executable. So now we can execute this, and look at this, we obtain our answer. Now this 10 was computed, why? Because in this final executable, the linker was able to inject the correct logic and was able to link the function, was able to recognize, look, this sum is implemented with this code. So that's the idea. And to achieve this, we need to reach the object unit. We need to compile the C into an object. And to do that, we need the header file. So if you're wondering why you need header files in Linux, it is because first you want to transform a C source into an object file. To transform into this object file, the compiler needs to know certain information about the function, like for example, how it is declared, basically, especially if you do not define it in your own source code. Like here, the compiler has no information about sum. So to obtain information about sum, we need to declare it. We need to declare it into the H file. Now the H files can be shared across unit of compilation, and then the linker will link together the different objects. And so basically that is the linker. We can link a single file with each other, but of course, if you link a single file, you're missing the point. Even with a single file, though, you are still linking with, for example, the standard C library. So you're still linked with something, but this is especially useful when you link with multiple object file. That is, when you have a complex program made up of different units of compilation of different C file and object file, and you want to link them all together to obtain a final executable. So basically the idea, and also by the way, here you can see that this is, for example, a dynamic executable. So this means that it is dynamically linked with the libc, which is found in usr libc.so.6. So basically that's the idea, and this works for all C programs. Now sometimes you have complex build systems, sometimes you have scripts in bash, sometimes you have make files. It doesn't matter the kind of build system that you use. At the end of the day, this is how the compilation process looks in C. And this is, for example, used in Doom. So here I have Doom, Linux Doom. And this is the original release of Doom, of the game Doom. And in one of the next video, I will show how we can compile this program from scratch, from the original source code, by making a few modifications to make it compatible with the current system. And basically, we're gonna see all of the stuff that I mentioned. We're gonna see object files, we're gonna see linking, we're gonna see the compilation of each single C into an object, and things of the sort. So if you're interested in that, please let me know. I will prepare the video on Doom, on compiling Doom in Linux. And basically, that's it for this video.